вообще, вот этот звук как сделать нормально? Я когда заходила, было очень да, первые две лекции, там что-то вообще как-то не помню.
Есть микрофон, а другого нет.
Ну ладно, здесь пытаюсь изменить конспект.
Он как-то с... Ну, где, видимо, телевизор.
So let us start the fourth lecture. Do you remember what did we have the previous time?
Well chambers, well group,
Yes, and
mental well chambers.
And dilemma that if we took the shortest decomposition, then we always have to send the last element to the negative one. We had dilemma that if we have an element of the wave group such that its shortest decomposition ends with some sigma alpha t, then the total element of the wave group sends alpha t to phi minus. Otherwise, the decomposition could be shortened. We will use it today. And also, we will use all the stuff we've had. Okay, so let me state the theorem which we want to prove today. Theorem. So, as usually, phi is our root system and delta is its base. This lemma has 5 parts. This theorem has 5 parts. First of all, suppose that we take any regular gamma. Irregular means that it is not orthogonal to any root. So gamma is regular. It doesn't belong to hyperplanes alpha orthogonal. Then it can be sent to the fundamental wave chamber. Then we can find an element from the wave group such that it will send our regular vector gamma to a vector which has a positive scalar product with all the simple roots. With all the simple roots. Okay? Is it clear? If we have our root system A2, I recall regular means it cannot be
Alpha from
yes. So I forbid all this stuff. I take any gamma, for example, here, and I know that I always can send it to this wave chamber. This is the third part. So it means that W acts transitively on the wave chambers.
we assume that delta is what two vectors in this picture?
This one?
Is it standard?
Yes, the standard one. One moment. This is the first. This is the second simple root. So positive with this one is this half plane, and positive with this one is this half plane. So this and intersected with this.
What is delta? What is sigma here?
Sigma.
The
Let us think. What reflections do we have? This is the mirror. We can apply the reflection along this mirror and it will send it here. Okay?
So in this example, sigma is vertical.
This is alpha
Vertical
1.
mirror.
Sigma alpha 1 works.
Okay.
The second part B. If we take another base, delta prime,
So what is x transitive?
it can send any element to any other element. In some sense, all the wave chambers become equivalent. So if we split the space into wave chambers, then we take any regular vector, we find the wave chamber where it belongs, and we say, okay, for some choice of delta, it will be in the fundamental wave chamber. So we make a change of basis, and we work with this gamma as it was in the fundamental wave chamber. This is the advantage. Everything is symmetric. Now if delta prime is another base, of our root system, then there exists sigma such that sigma maps from the group. Sigma maps delta prime to a delta. So here we have endpoints and here we have n other points. Okay. So W acts transitively on bases. So all the bases are equivalent after the section. Now, any root can be simple. If alpha is any root, then we can find such a sigma so that sigma applied to alpha will belong to our simple root system. There are no bad and good roots. Any root can be a part of a base. Okay. Now, what we want last seminar, W is generated by the simple reflections. So by the sigma alpha from our base. And now the last is if some element of the whale group leaves our base in there, and then in fact it is the identity element. So in other words, we can say that W acts simply transitively. Okay, so this is the same said by words of the formulas. That says it acts simply transitively.
What is simply transitive?
Просто transitively. So this is the term which means that there are no stabilizers. This action is without stabilizers. And there is the bijection, the orbit of any element can be labeled by the element of our group. So we have 6 elements in our group and we have 6 whale chambers.
By first implies that WDX transitively chambers. Transitive, we can any whale chambers go to another.
Yes.
And why
So
it means
take
that?
any whale chamber.
Okay.
What is any whale chamber? In this picture,
Yes.
this is taken as any whale chamber.
Uh-huh.
So it means that its interior is the set where we can take our gamma.
Yes.
Take any gamma from its interior. We'll find sigma such that
Yes.
sigma from gamma is mapped to the interior of the fundamental whale chamber.
Yes.
If we move gamma inside this interior, all the signs plus with this root, minus with another root, etc., it will remain unchanged. And if we apply some sigma, it also will remain the same. So if we take any gamma and any gamma prime, we take sigma gamma, and if I take sigma alpha 1 gamma prime, it will belong to the same whale chamber because elements of the whale group preserve our scalar product. Okay?
Может по-русски.
Можно. Еще раз, вас смущает, почему, если я докажу вот это, то
Да.
надо...
Почему вот если мы в одну конкретно отправить, то мы в любую можем отправить?
А, вас этот момент смущает?
Да.
То есть, хорошо. Это автоматически, в смысле, сейчас, это стандартный ход. Если вы можете взять вот здесь камеру Вери, здесь их перевести вот в эту, то одним элементом эту сюда, другим вот эту сюда, тогда ЖЖ в минус первой, да.
Сейчас мы доказывали, да, что типа, вот такая только одна.
Какая такая?
Ну вот это фундаментально у нас называется.
Фундаментально задается понятно, каким набором неравенств.
Да? Ну вдруг мы в разные фундаментальные провели.
Нет,
только
она одна. В смысле, это просто набор неравенств. Фундаментальная — это такая, где вот гамма с альфа больше либо равна нуля для всех альфа из нашей системы простых корней. Мы просто написали, сколько это неравенств. Почему она связана, мы не доказывали, но потому что любое полупространство содержит, ну, оно выпуклое, содержит отрезок, либо с двойной точностью содержит отрезок. Что-то надо еще? Вроде нет, не хватает. Any questions? Do you have any questions? So we switch to Russian just to explain transitivity. Okay.
Сейчас. Транзитив, фундаментально это вот чтобы скалярное произведение было больше нуля.
Да.
Почему она одна? Мы это доказывали? Или это очевидно?
Ну, это очевидно. Еще раз. Что такое фундаментальная камера Велли? Это множество, которое задается n неравенствами в размерности n. Ну, то есть, если вы берете на плоскости как бы две прямых, да, говорите, вот берем вот эту полуплоскость, да, от этой прямой, а вот от этой прямой берем вот эту полуплоскость. Почему, как бы, ну, это вам задает некий конус, у которого, ну, после афинного преобразования будет стандартный октант. Тут то же самое, у вас n неравенств, которые после какого-то афинного преобразования дадут стандартный октант. Просто вы задали неравенство, и все. Это множество связанное, выпуклое, как бы хорошее. То есть, если мы говорим, что камера Велли — это компоненты связанности того, что получается, если выкинем все зеркала, то тут таких проблем не возникнет. Okay. Then I'm planning to prove this stuff. If you don't believe me, maybe I should check this by hand during the seminar. I just think it should help. So, for the proof, the plan is as follows. For A, B, and C, I want to take W prime, which is generated by simple reflections. It is generated by sigma alpha, where alpha is taken from our base. Okay? So, as we will show that W prime equals W, but right now I will use only this one. This group will be enough. Okay. Do you remember I defined the following reaction delta, which is 1/2 of the sum of all positive roots. The sum of all positive roots. So,
what is ABC?
A, B, and
Oh,
C will
okay.
be proved for W prime.
I thought these are very.
I just want to prove that W prime acts transitively on all this stuff. Okay. So, we took a regular delta, gamma, so for all elements sigma from delta prime, we can find what will be sigma applied to gamma multiplied the scalar product with delta. This is a finite number of non-zero values. Of non-zero? No, of some real values. Okay? So we can, there exists sigma which maximizes this such that is maximum. So we can fix it. Okay,
Sigma from double.
from W prime. Um, okay. What can we write? Let us take alpha from our base, then we can say that if we add one simple reflection, we will stay in W prime. This was from W prime. We added one simple reflection. We're still in W prime. But now we can say that the scalar product, which was maximized, it was greater or equal than, apply this to gamma and take the scalar product with delta. Okay? It is just because we have maximized that scalar product. But now we can move sigma alpha here. Sigma alpha square is identity. So this is just equal to this multiplied by sigma alpha delta. Do you believe?
Because sigma is orthogonal.
Yes, sigma alpha is orthogonal and sigma alpha square is the identity. Do you remember what is sigma alpha applied to delta?
Delta minus alpha.
Mm-hmm.
Delta minus alpha.
Yes, sure. So this is and now we can rewrite it as sigma applied to gamma delta minus sigma gamma alpha. But so we are done. We found sigma which maximizes some scalar product, and now just because of the inequalities, sigma applied to gamma scalar product with alpha is non-negative.
Why it cannot be zero because gamma is regular.
Gamma was regular, yes. So if sigma gamma alpha is 0, then sigma alpha is 0. Sigma alpha is another root, and gamma is not regular. And we're done. So we found sigma, which maps gamma to the fundamental Weyl chamber.
Can you just explain this gamma again?
Hmm?
When you said there exists a gamma, so is that this inequality holds?
No, why there exists a gamma? We took a regular gamma.
Yes.
then we found sigma, which maximizes this scalar product.
No, it is an exercise.
No, this is a finite set of points. Just the number of all possible values of sigma is finite. They're taken from W prime. W prime is finite because
This is
it is the subgroup of the Weyl group, and the Weyl group is finite because it interchanges the finite set of points. So the choice is we choose sigma. Maybe I should erase this one. There exists sigma from W prime. Okay. So all this explanation is that this sigma indeed works. If sigma maximizes this scalar product, then it maps gamma to a vector from the fundamental Weyl champ. And we have proved the A. Okay. Any questions? Now then we proceed. Let us prove B. So that was for A. Now B. Proof B. Suppose that if delta prime was constructed with gamma prime, 2 lectures ago we proved that each base is constructed with respect to some gamma. Okay. If gamma prime was constructed using gamma prime, there exists by A there exists sigma such that sigma of gamma prime equals gamma in the fundamental Weyl chamber. And if we take gamma from the fundamental Weyl chamber, then the base we construct with it will coincide with our initial base. Это магия. Давайте я по-русски скажу. Еще раз утверждение, которое мы 2 лекции назад обсудили. Если вы берете гамма из фундаментальной камеры Вейля, то получаемая по ней получаемая система простых корней совпадает с вот этой вот. Просто потому что как бы с плюсиками будут ровно те векторы, которые по этой дельте раскладываются с положительными коэффициентами. А тогда среди них неразложимые как раз и будут как бы дельтой. So should I repeat the explanation? If gamma is taken from the fundamental Weyl chamber, then if we construct the base in the positive semi-space according to gamma, it will coincide with our delta. It will coincide with the delta which we have fixed at the beginning of the theorem. Do you understand it? Okay. Александр, верите вы нам? Хорошо. So, yes, I almost explained that sigma applied to delta prime equals delta. Delta, delta, delta. B is proved. Can I proceed, or do you have any questions?
Сигма у нас откуда?
In this part, we took sigma from W prime.
Б. Что сигма она отдельно? W prime?
Since we use A, it is in W prime. Yes. It is in W prime. But it suffices because we claim that it is from W. W prime is a subgroup of W. Soon it will become W.
Значит, смущает. У нас гамма, он как бы фиксирован. А гамма аут.
Где гамма фиксирована? Ну, не совсем. Где гамма фиксирована?
Сейчас, тогда мы куда это вообще? Сейчас гамма это то, чем порождена.
Ну, я не фиксировала в этой теореме такую гамму.
Сейчас вот мы когда говорим, что существует сигма, что сигма от гамма штрих это гамма. Вы куда тогда?
Зовем гамма.
Гамма это как бы порождающий дельта или что?
Да.
А.
Ну, простите, в части А у нас уже была гамма, которая лежала вообще в какой-то левой камере Вейля. Если уж так вот следить, чтобы все гаммы были в фундаментальной камере Вейля, надо было вот здесь в доказательстве еще одну букву заводить новую. А я этого не сделала. Сейчас тут есть возможность копировать?
Да, выбрать.
Сейчас попробуем. Я не включилась. Сейчас еще раз.
Не запомнил.
А?
Не запомнил.
Попробуй еще. Ладно, быстро. Вот. Копировать, да?
Она сразу сюда вставилась. Вы назад перенесите. И... Ну, возможно, она все еще скопирует.
Сейчас попробуем.
Наверное, надо просто тыкнуть.
Ну, нет. Хорошо. Okay, so now we're going to prove the part C of the theorem. I was unable to copy it to this blackboard. So our aim was to prove that any root, so at the moment alpha is not simple. We want to show that there exists sigma from W prime such that sigma applied to alpha is simple, belongs to our fixed base. Okay. So we've had some preparation last seminar. Yes. Do you remember we've had gamma prime, which was in H alpha, but not in not the H beta or beta, not plus minus alpha. So we can find such a gamma prime, which will be in H alpha, but not in all the other mirrors. This gamma prime is not regular. It is not regular, it belongs to a mirror. Maybe I should draw something. So this is our gamma prime. Okay. we move it a little bit. Scalar product is a continuous function. If we move it in one direction, it will become positive, and on the other direction, it will become negative. So let us choose the direction, take gamma in such a way that gamma alpha is positive. Gamma alpha, it is very small, we call it epsilon, and it is positive. So gamma prime alpha is 0. So we can take epsilon very small. What is very small for us? We want the epsilon to be smaller than gamma. I can try gamma prime beta, like this, for example. Just to be safe, I add 1/2. Maybe just gamma prime beta is enough. Okay. What does it mean if we move it a little bit? Gamma beta. So for all beta not equal to plus minus alpha, gamma beta are strictly greater than epsilon. Okay. This is what we want. Gamma alpha equals epsilon, and gamma beta is its absolute value is greater. Okay.
We understand it, or we will prove it.
It is by continuity. When we sit here at this point alpha prime, no, gamma prime alpha is 0, and all the other values, it is a finite number of non-zero values. Okay?
Типа мы в другую сторону. Типа тут мы взяли меньше половинки, значит там больше половинки.
Да, да. И мы не испортим это условие. Да. То есть мы можем вот в эту сторону пойти совсем чуть-чуть, вот совсем чуть-чуть. Вот эта вот штучка будет совсем маленьким эпсилоном, а вот эти вот все мы не сильно испортим. Okay, this will be our gamma. Now gamma is regular. So all these scalar products now are non-zero. They're still non-zero. And this one will become non-zero. So now our new gamma is regular. How can we find a base if we start with gamma? We take gamma plus, and we take all the indecomposable vectors, as 2 lectures ago. But you see that this one will be the smallest scalar product. So alpha will be indecomposable in this, so in gamma, phi gamma plus. Yes, it was phi gamma plus. In phi gamma plus, alpha will be indecomposable. Because if we decompose it using some betas and then take scalar product with gamma, we will have too much. So f is indecomposable. So what did I want? I wanted, yes, just so alpha belongs to the base which we denote by this. Okay, and we know that by b. Any question?
I don't get the last argument. I got that gamma is chosen in a certain way, then you're claiming alpha is indecomposable.
It was 2 lectures ago. It was our plan. When we said that each base can be obtained in the following way. I need once more to draw A2. So let me draw A2. We said that gamma. So for example, what if we take gamma equals 0, this scalar product with gamma equals 0. Suppose that we take this semi-space. Then this vector can be expressed as the sum of this one and this one. So it is decomposable. And these two vectors are indecomposable. So this is the set of simple rules which were constructed using this gamma. So they give scalar product with gamma, which is positive. And among such vectors, among these 3 vectors, they cannot be expressed using all the other vectors from here. And we explained that each base can be obtained this way. If we start with a base, for example, if we start with this random stuff, we say that there is this part which is positive, this part which is positive for this vector, this which is positive for this vector. We take some regular gamma from here, then the scalar product with this is positive for, which is on the left of this red line. And this will be our positive root, and the indecomposable one from here will be this base. This is the projection between bases and wave chambers. But now some more idea. If we decompose one vector using, for example, this one is expressed using these 2 ones, in this equality we can multiply all the stuff, take the scalar product with gamma. We will have some sum of positive real values. So if alpha is expressed in some betas, then we take the scalar product with gamma, and we know that epsilon is expressed in some positive numbers which are greater than epsilon. It is not possible. So alpha cannot be decomposable in this situation due to our choice of gamma. So it is indecomposable, and it will be included in delta gamma. By B, there exists sigma from the W prime, sigma which maps this base to our delta. So delta, so sigma alpha will belong to delta. And we are done. Any questions? Ну да, немножко тяжко. Окей. Then,
Можешь это все ради пункта D?
ну это все ради всего. Подождите, ну как бы вам не кажется странным, что все такие: «Ой, система простых корней, какие-то таблицы пишут, а вдруг они здесь принципиально разные?» Давайте, раз все заснули, я сейчас это вопрос. So I just want to explain why this is very important. So if you take any textbook on the algebras or on the groups, it has some tables. So these are some rules, some simple rules, etc. All this stuff is possible just because all the simple root systems, they are all equivalent. So you can say, let this be some canonical choice. It has so the next table will be about representations of the algebras, and it will also use these simple roots. So any choice is okay. So any choice is equivalent to this choice. So this is very important from the conceptual point of view. If you want to classify all the representations of the Lie algebras or Lie groups, they're labeled by highest weights, and highest weights have to do with the choice of simple roots. So they can be extremal weights, but your choice of the highest weight is just your choice of delta. Okay. So let us prove D. Here. Our aim is to prove that W prime equals the W. So our aim is to show that for any root so we know the W is generated by a sigma alpha. So if we show that sigma alpha belongs to W prime, it will be enough. But by C, there exists sigma from W prime such that sigma maps alpha to some beta from our fixed base. No, let me use W here, as in the previous seminar. Let it be W. W and W. Then sigma W alpha. It will be W sigma alpha W minus 1, as in the previous seminar. Okay? Just to conjugate with some automorphism. But now we know that this is beta, this is from delta, so this is from W prime. We can express sigma alpha is W minus 1, sigma beta W, which clearly belongs to W prime. W belongs to W prime by construction, and sigma beta belongs to W prime since it is a simple reflection. So we have proved B.
Что сигма бета W prime?
Какое место?
Что сигма бета W prime?
Это простой корень. любое проведено картинное отражение. Мгм. Хорошо. Any questions for D? Мгм. Что это было? Я не поняла. Я-
Ну, он в фокусе
Any questions? So let us prove E. So let sigma fix our base, but suppose that this is not the identity. How can we obtain a contradiction? Let us express sigma as a verb of minimal length. So express sigma as a product of simple reflections So we can use our lemma from the previous lecture. So sigma equals sigma 1, etc. Sigma t. But then sigma applied to alpha t belongs to V minus. So sigma applied to alpha t can belong to our base. And when now? Do you need any more explanation?
Как из того, что сигма отправила архетип в отрицательный поле.
Да. А смотрите, вот сигма должна была перемешивать положительное и отрицательное.
Архетип это
Мы называем простые отражения. То есть эти все альфа, то есть сигма int это сигма альфа ita. Альфа ita from is delta. Do you understand? So is the can I explain in Russian? Or do you need that I explain in English?
You can explain this.
Yes. So what was the notation last time? Sigma I was the simple reflection sigma alpha I. And we said that alpha I could coincide. So sigma I is in fact sigma alpha I.
Yes.
And all in common we can have the same alpha I but not close to each other. So what next? By our lemma from the previous lecture, this should be negative. Otherwise, the word can be shortened. But now, what is sigma alpha t? Sigma applied to any simple root should be a simple root. So sigma alpha t should also be from delta. But on the other hand, it will be negative. So negative is on one side, delta is on the other side. So it cannot happen. So, very good.
So how can we summarize it, this theorem that all bases is equivalent
Yes.
and well group is generated by simple reflections
Yes.
and it acts simply transitive on the well chambers.
On the well chambers and on the bases. Yes.
On the well chambers it also acts
Yes.
simple.
It acts simply transitively on the wave chamber because each wave chamber is a base. It gives you a base. Any gamma from this wave chamber gives you the same base. Okay. It is really important, but maybe a little bit technical. Can we continue?
Yes.
Now, length of an element from the wave group.
А как это по-русски? Simple transitive.
Просто transitive. Это где-то было в самом начале, когда про действие групп говорите. Просто это не всегда нужно. Многим людям это не нужно. So length of an element W from, or sigma from W. So spoiler that if you take the symmetric group action, it is the same notion of length which was defined for the symmetric groups. So if we express as before, we can express sigma as sigma alpha 1, sigma alpha 2, etc. Sigma alpha t with p minimal possible. And alpha I are simple roots. So each such expression is called reduced. So reduced means that the length is minimal possible. And let us define L of t, the length of L of delta. I'm sorry, the length of the length of an element sigma is this value of t. Okay, and by so the length of the identity we set 0 by convention. Surely length is defined when we have fixed this system of simple roots. For another choice of delta, it can become different. Okay, now let us also define n sigma. And sigma, it will be, in some sense, the number of disorders. So the number of positive roots which become negative. So for which sigma of alpha belongs to phi minus. And so lemma for all sigma, we have L of sigma equals N of sigma.
Number of positive roots alpha for which sigma of alpha is
Yes, alpha. So alpha from 5 plus positive. We have seen this lemma for length 1. Let us discuss this lemma for length 1. So example for the lemma. If L sigma equals 1, what can you say about sigma?
It is a simple reflection.
Yes, it is a simple reflection. And it says that a simple reflection sends only one positive root to the negative part. Do you remember this? Then I can draw A2, maybe AE, maybe B2. So what is a simple reflection? Let us say that these are simple roots. Then the simple reflection corresponding to this one, this will be sigma alpha 1. It sends this positive root to the negative one, and it mixes up all these positive roots which are not alpha 1. So only alpha 1 is mapped to minus alpha 1. Okay? So last time we proved that sigma alpha maps alpha to minus alpha, and it mixes up all the other positive roots. Since there were coordinates in the basis, and at least one coordinate remained positive. Sigma alpha subtracts several copies of alpha. And if we've had a coordinate along another beta, it remains positive, so the vector remains positive. Помните, было дело? В прошлый раз была лемма, как мы ее доказывали, что сигма альфа перемешивает все положительные корни, которые не альфа. Там просто было написано, что в координатах пускай, значит, да, сигма альфа выбрасывает сколько-то с каким-то коэффициентом альфа. А при каком-то другом простом корне был положительный коэффициент, и он не поменялся. Значит, сам вектор остался положительным. So, in fact, we have proved this lemma for L sigma equal to 1. And for 0 also it is obvious. So we can proceed by induction. So to prove it, we use induction on the length. Induction on L sigma. So we need to prove the step. Step assume that it is true for all tau such that this is tau, such that the length of tau is less than the length of sigma. So that sigma d sigma alpha 1 d sigma alpha t be the reduced expression. And now we can take tau equal to sigma alpha t. Is it clear that the length of tau is less than the length of sigma? Is it clear? We just forget the last one. We forget the last simple reflection.
Yes.
Okay. Now what happens with positive roots? We know that if we apply first sigma alpha t, it maps alpha t to the -1, and it mixes up all the other positive roots. We know that by the induction hypothesis, we know that n of sigma alpha t equals t minus 1.
Yes.
And so, what is n of sigma? We just check which ones are mapped to the negative ones. Clearly, alpha t is mapped to the -1 because we have had a reduced expression.
Yes.
Now, what about all the other ones? First, we apply sigma alpha t. They are mixed together, but they remain positive. And then we apply tau. We know that tau sends exactly t minus 1 positive vectors to the negative ones. We know that tau sends alpha t to the positive one, so it doesn't matter. So we have proved this lemma.
Can you repeat the last argument? I didn't get it. Up to this is clear. The 10 of sigma alpha t is t minus 1. And then you concluded that
Yes, if you want,
the extra root is alpha t, right?
I need another blackboard. Just, unfortunately, I cannot copy from one blackboard to another one. So, what happens? Once more, we have our root system. So we have for sigma, we have a reduced expression which ends with
Sigma t.
yes, sigma alpha t. So for me, this is alpha t. This is alpha t. Now all this stuff for me will be called tau. For tau, the induction hypothesis
Is true.
is true. What next? If we want to check where tau maps alpha t and phi plus without alpha t. So we know that tau of alpha t, it should belong to phi plus
Yes, and somewhere positive.
by last time, since that was a reduced expression. Now we know that all in total tau sends t minus 1 positive vectors to negative ones. So t minus 1 vectors go to phi minus. All the rest vectors, they stay in phi plus. I write exactly t minus 1 because this one didn't go to phi minus. So here exactly t minus 1 went to phi minus. Now let us check all the same check about sigma. First of all, sigma applied to sigma. This would be, let's just rewrite it for you. It is sigma equals tau sigma alpha t tau sigma alpha t applied to alpha t. This is a minus tau applied to alpha t. This is the minus which sorts out. So this is exactly minus alpha t. So we know that tau of alpha t belongs to phi plus, then this belongs to phi minus, definitely from phi minus. And now if we apply tau composed with sigma alpha t to phi plus without alpha t, we know that sigma alpha t is just a permutation of this set. This is the permutation of this set, and then tau sends exactly t minus 1 vectors to phi minus. T minus 1 vectors go to phi minus. All in total, we have t vectors which go to phi minus. Do you believe?
Тау это альфа-ти плюс.
Смотрите, тау. Тау — это когда мы взяли от приведенного выражения сильно последнее простое отражение.
Почему тау это альфа-ти плюс?
Смотрите, это было в прошлый раз. Мы сказали, что если бы оно было минус, мы бы приведенное выражение сократили. Я вроде не должна, у меня светится сознание, но вроде как раз сейчас неправильно. Да. Ну, хорошо, что время? Есть еще приведенное выражение?
Надо есть.
So I'm able to understand one more lemma. Да. Еще одна lemma. Нормально? Или я всех уже вырубила?
Нормально.
Нормально? Ладно. Еще одна lemma. Okay, then the last lemma for today. It says that in fact no, I just changed the lemma. all the extension within the sheet. So suppose that lambda and mu be 2 points from the closure of the fundamental wave chamber. So this is the closure of the fundamental wave chamber with the mirrors which with the mirrors which form the boundary. Suppose that some element, if sigma alpha equals mu for some sigma from our wave group, then the sigma is a product of simple reflections. Which fix alpha. Which fix lambda, and in particular,
Извините, можно у вас на минуточку будет хлеб?
давайте я закончу сейчас, через минутки клип я закончу, и тогда да. So in particular, we will have that these 2 points coincide. Which does it mean? So it says about the closure of the wave chamber. If the wave chamber was something like this, we have seen this for the interior points. And now we show that we're going to show that, for example, 2 points from the other from 2 different boundaries cannot be mapped one to another. So they're always in different W orbits. Okay?
And we will prove it.
Okay, if you are tired, we can just state it.
Все.
No, this is not an exam. This can be done as an exercise during the seminar. So in high dimensions, we will have walls of different dimension. So each wall is a vanishing of one scalar product. So we have always walls. So the points where one scalar product vanishes, then if we take 2 simple roots, there is an equation that 2 scalar products vanish, etc., etc. So for the point which sits on one H alpha, there is only one sigma which fixes it. Reflection on this alpha. And if it is in the product of 2 walls, then there is the whole finite group generated by these 2 reflections which fix this point. So it has its own life form and its own intersection. Okay, then I think I will stop here. Thank you for your attention. Устно. Чтобы с вами поговорить, что никто что не понял. Ну вот как бы есть я, есть Вадим, по идее. Можно у нас ловить и пытаться задавать. Если вы как бы совсем все плохо, вы просто приходите и начинайте разговаривать по-английски, мы вам поможем. Если не все плохо, то просто задавайте нам задачи. Там вроде достаточно простого.